Hello ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be going over the ideal gas law, so make sure that you follow along in your note packets, and if you have any questions you ask tomorrow. Alright, so getting back to gas laws, we talked about the combined gas law, and so the second most important gas law is called the ideal gas law. Now here's the thing about the ideal gas law. Avogadro, yeah, that same exact Avogadro, discovered that if you know the volume of a gas, it is proportional to the number of particles in that gas. And so remember, we get sort of the term mole, and normally we associate with Avogadro, but this is technically what his big discovery was, is that there's a connection between the volume of space that something takes up in a gas and how many particles you'll find, so the number of moles. And when you work this out, what you end up with is realizing that there is a proportionality between the volume and the moles, and that is a constant. Okay? So if you know the volume that a gas takes up, and you know the number of moles that are inside of that gas, when you divide them by each other, you get the same number over and over and over again, and it's a constant. We call this Avogadro's law, and an actual way of writing out Avogadro's law is like this. So if I take the volume and I divide by the number of moles, I get R. And so R is a constant. Here's the interesting part about this. The ideal gas constant has like the most insane units that you'll ever see in all of chemistry. And so even though we abbreviate R as the universal gas constant, there are many different variations of it. Okay, the one that we're going to be using is this guy right here. Okay, so what is R equal to? What is this constant that we keep getting over and over and over again? Well, we get 0.082. Now that's only with particular units, which is why right here it says notice and memorize the units. Notice and memorize these units. Liters times atmospheres over moles times Kelvin. Again, the most disturbing array of units that you'll ever see in a row here, and I'm going to write them out. So we have liters times atmosphere divided by moles times Kelvin. So what's important here? Well, I have a unit of volume up here. I have a unit of pressure up here. I have my, amount of a particle, or amount of particles, sorry, and then I have my temperature. So the four major units that we use throughout, sort of the year are all summarized in this gas constant. So 0.082 is a constant that is only true with these units: liters, atmospheres, moles, and Kelvin. If we change the units to something else, like if instead I want to use milliliters, or I want to use torr, or I want to use Celsius, then this number will change. Okay, it's not, it's not something that won't move around depending on the units I use. This constant is only true for this series of units. So why is this constant important? Well, when I combine Avogadro's law and the combined gas law, I get the ideal gas law, and this is the ideal gas law. PV equals nRT. And so again, just kind of like please vomit over the toilet, the way to remember this is don't be a pervnert. PV equals nRT, pervnert, okay? And so why is this important? Well, think about the units that my constant had, and think about these guys all the way up here. So what is pressure? Well, that's atmospheres. What is volume? I can measure that in liters. What is N? That's the number of moles, so I can say that's moles. And then what is T? Well, that's just Kelvin. Notice that right here, this guy has units that look an awful lot like this. Why? Because pressure is measured in atmospheres, volume is measured in liters, number of moles is measured in moles, and then we have T for temperature measured in Kelvin. So it's not a random array, it actually is very specifically chosen. So what are some important applications of this ideal gas law? Well, remember, this is going back a ways, but we said that molar volume is equal to 22.4 liters at standard temperature and pressure. Well, where did we get 22.4 liters? I told you it's an important quantity and that we were going to talk about it eventually. Well, we're talking about it now. Let's plug in values for PV equals nRT and see what we get. All right, so let's say my pressure, I'm at standard temperature and pressure, is 1 atmosphere. So I have 1 atmosphere. My volume, I don't know. N, okay, that's the number of moles. Since I'm looking at molar volume, I only have 1 mole. And then R is 0.082. I'm not going to include the units merely because, well, you understand, I can't really write all of those down and fit it in here. And then T is going to be standard temperature, so that's 273. That's a 7, 273. So solve for V, and what do you get? You get about 22.4 liters. This equation right up here, this extremely important equation, is where we get 22.4 liters from. That's where we get the molar volume from. It's not from, some sort of like magical land of mystery. It's actually from just simple algebra. And so in this space that you see, prove to yourself, copy down that math and show that it is 22.4 liters indeed. Important, the units of R. In order for units to cancel when we're using the ideal gas equation, we need to have atmosphere for pressure, liters for volume, temperature has to be in Kelvin. So we've gotten into the practice of converting everything into Kelvin, but now we need to get into the practice of converting everything into liters and into atmospheres if it already isn't. We spent a lot of time already talking about pressure conversions and doing pressure conversions. This is the reason why. And hopefully you can convert between milliliters and liters because it's not exactly that difficult. But remember, we need to be able to use R as being 0.082. So we need to have these units. These are not optional. If I don't convert things into these 3 units, then I won't be able to actually solve my equation. So when are we going to use this law? So the last time I said anytime you had different pressures, temperatures, or volumes, we were going to be using the combined gas law. Well, this is our other important gas law. The only time we're really going to be using this is anytime it mentions moles or if you're asked for moles or grams of something. Okay? Why? Because PV over T does not have moles in it. And so because this is our only equation that has moles in it, it makes sense that we'd have to use PV equals nRT. That's the big difference there, N. Okay? Now, in case you forgot, remember, if I'm converting from moles to grams, I multiply, and if I'm converting from grams to moles, I divide. So remember, got to still be able to find your molar masses of things using the periodic table. Now let's practice this. Here's a really good example. A sample of hydrogen gas has a volume of 8.56 liters at a temperature of 0.00 degrees Celsius and a pressure of 1.5 atmospheres. How many moles of gas were in this sample? Well, let's underline all of the key information since that's going to be my go-to thing. So, I have a sample. It is hydrogen gas. My volume, 8.56 liters. My temperature, 0.00 degrees Celsius. My pressure, 1.5 atmospheres. And what am I looking for? How many moles? So PV equals nRT. It mentions moles. I need to use this. Okay, so how am I going to plug in and use all of this information? I need to make sure, first of all, though, the very first thing I do is, do all of these match the units I need? Well, luckily, I've got liters here. I've got atmospheres here, so those are taken care of. The only thing that's not is, well, as we figured, degrees Celsius. So I'm going to cross that out, and I'm going to make that 273 K, because that's what 0 degrees Celsius is equal to. Now all I need to do is plug all of this in and solve for my variable. So let's plug everything in. So pressure, I have 1.5 atmospheres. My volume is 8.56 liters. Okay? Equals N. N is what I'm looking for. I don't know what N is. Okay? R, 0.082, and then 273. So if I'm solving that, I got to get N by itself. I would divide by this. I would divide the other side by the same amount. Okay, and then notice these would cancel away. And so in your calculator, what do you get N to be equal to? N equals about 0.57 moles. Is that a reasonable answer? Yeah, I guess it's a reasonable answer. It kind of makes sense. And so if you got anything different than this, then it's probably because you plugged in something in the wrong spot. But again, PV equals nRT, not exactly a very difficult algebraic equation to solve. You will be given pieces of information. You'll be given 1, 2, 3, in this case, 3 pieces of information, and you're looking for another. You're looking for this guy right here. Last but not least, let's try this example. So, example, a sample of nitrogen gas, N2, has a volume of 1.75 liters at standard temperature and pressure. How many grams of N2 are in the sample? All right, let's think through this. So let's underline our key pieces of information. I'm talking about nitrogen gas. I have a volume of 1.75 liters. I'm at standard temperature and pressure. So what is that? That's 1 atmosphere, and that's 273 K. How many grams of N2 are in the sample? That is what I'm looking for. How many grams are there going to be? Now, what am I going to use? Well, PV equals nRT. Why? Grams is mentioned. Anytime I see grams or moles, I'm going to have to use PV equals nRT. Now, the next thing I should do is make sure that my units are correct. Let's look at volume. Volume, yep, in liters. Standard temperature and pressure, well, I wrote them in atmospheres and in Kelvin. So it looks like we're all good. Let's plug in our values then. All right, so I have 1 atmosphere. That's my pressure. I have 1.75 liters. N, I don't know. That's technically what I'm going to need to find. 0.082, and then 273 K is my temperature. So how did I know I was trying to find N here? Well, anytime I'm asking for grams or for moles, I know that I can convert between those two, and so that would be my unknown. If I'm asking for grams, I'm still going to have to solve for moles before I can do any gram conversion. All right, let's plug that into our calculators, and let's solve for this. So I've got dividing by 0.082 and 273K and all that stuff. I do the same thing to the opposite side. Okay, my writing is getting worse. I hope you're still able to read it all. I hope so. And then that would go away, and I'd be left with just N. And so when I plug all of that stuff into my calculator, and this is really going to bug me, so I'm going to make that a clear 0. When I plug that into my calculator, what do I get? I get a number that is about 0.078 moles. All right. Now the interesting thing is that that is not the answer though, because I'm asking for grams. So how can I convert from moles of a substance to grams of a substance? I'm going to need to multiply by the molar mass of nitrogen, which is N2. So let's do that up here at the top. Okay, so I've got 0.078 moles, okay, and that's of N2. And so if I want to convert, I would need to multiply that by 28 grams in 1 mole of N2. And when I do that, I get about, as you can probably see, about 2.2 grams. Okay? And why did I have to do that? Well, I wanted my moles to cancel, and so yes, you still have to be able to convert between moles and grams and moles. And that's how I would solve this question. Okay, so there was a lot going on in this one. We had standard temperature and pressure, we had mole conversions, all things that technically I need to remember, in addition to PV equals nRT. So again, if you have any questions, make sure you ask tomorrow.